All right, so in this problem, again, we have kind of a simple supported beam. And oddly enough, again, we're looking for some cut at C, kind of more towards the left. But this time we have a linear distributed load, triangular shape. It really shouldn't affect our analysis. We're still going to cut the structure at C, because that's where we want the internal forces. And now you have to decide whether you work the left side or the right side. Now, in terms of reactions, again, I think it's a wash. Left side, you'll just need 1. Right side, you'll just need 1. So no advantage there. But when you go to break down this distributed load and you're working the left side, what do you have? A triangle. The right side, you have a trapezoid. Trapezoids, by their nature, are more complicated than triangles. So, when possible, I would go for the triangular side. Sometimes you don't have a choice. And if you do go for the trapezoidal side, don't forget, you can break it up into 2 forces. One for the rectangular portion, and then another for the remaining triangular portion. It's not terribly hard, but that's just one less thing you have to do, so I think we should go left. So with that said, I'm going to assume that I have a reaction at A in the Y and in the X direction. I would also have a reaction at B. But since I'm just going to work this side of it, I only need my reactions at A. So just like the previous problem, if we sum moments at B, we should find our unknowns at A. So I'll do that. So I'm going to sum moments at B and make sure that's in equilibrium. Now right away, we're going to have to deal with this triangular load, but the whole triangular load for the reactions. So remember, the area of a triangle is 1/2 the base times the height. So in this case, the base is 18, the height is 3, so that'll be 27, right? 1/2 base times height, that's not, yeah. And it's going to act at the centroid of the triangle. And the centroid of the triangle is always 1/3 the distance from the higher end, the bigger end. So 1/3 of 18 is 6 feet. So this will be 6 feet from B. And that's all I'll need for my reactions right now. Everybody see that? Any questions about that? So summing moments about B, this concentrated equivalent force is going to create what kind of moment about B? Positive or negative with right-hand rule? Positive. So I've got a force that's 27 kips. The distance from B to the centroid where the force is applied is 6 feet. Then the next thing I have is way over here my A reaction, which is going to create what kind of moment? Negative. And that'll be AY, and the distance from B to A is 18. So it looks like AY is going to be 9. Now, since your load is shifted heavily to the right, you'd expect BY to be way bigger than AY, probably twice as big, and it is. You can see our AY is going to be small. If we did find BY, we'd find out that it was 18. That makes sense. Seems reasonable. So now I want to come down here and draw my free body diagram for the section from A to C. And again, to help us out with that, I'll draw it a lot bigger. And we'll start at A. I know AY is 9, and I zoomed up and got a positive value, so I know it's 9 kips there. And then I've got to deal with this triangular load. I know this distance is 6 feet. What's the magnitude of this triangular load, the intensity of this triangular load here? Yeah, well, I know that all the way over here at 18, it's 3. So what's the slope of that line? Rise over run, right? That's 3 over 18. That's 6. So that's a slope of a 6. And if you go over 6 feet, 6 times a 6 is 1. So this should be 1 kip per foot. You could also do similar triangles, right? This height is to 6 as 3 is to 18. Either way you get it's 1. I know it's simple geometry, but you'd be surprised how many students don't get that right. So think about it and make sure you step in the right direction there. Why is that going to be important? Because to find the concentrated equivalent of this load, I need that intensity. So again, it's triangular shape, so it's going to be 1/2 base 6 times height 1. That's going to be 3. And it's going to be, again, 1/3 the distance from the big end. 1/3 of 6 is 2 feet. And then at the cut surface, I'll assume positive shear force, positive axial force, and positive bending moment. And from this point, it's pretty straightforward. Just use your equation. So we'll start with the one that we always like to do first, that works best. We'll sum moments at the cut. Make sure the whole structure is in equilibrium. Again, I like to use right-hand rule. So the moment here is positive. The concentrated equivalent force 3 kips about C is also positive. So that'll be a force of 3 kips and a moment arm of 2 feet. And then way over here is the 9 kip force. What kind of moment is that creating? Negative. So the force is 9. The distance is 6. So when you solve for the moment at C, it looks like I get 48. You guys get 48? Positive 48, I think. Positive bending moment at C. Does that make sense? I don't know. Let's go back. How is this thing going to bend? Probably something like this. Is there going to be negative bending moment anywhere in that structure? No. So if you compute one, you've made a mistake somewhere, either calculation or conceptual. And then we can finish it by summing forces in the y direction. I'll assume up is positive, so my shear force is down. That would be a negative force. My concentrated equivalent is down. That's a negative force. My reaction, 9 kips, is up. That's a positive force. So I solve for the shear at C, and I get 6. It's hard to see whether it's positive or negative shear. But it is positive shear. So any questions? That one only took 8 minutes. Wow, we're getting faster at this. So guess what you're going to get for homework? 3 of these. Should I throw in another SAT problem just for fun?
No, please don't. No.
Okay, I will. Since you asked for it. If you just said, yes, we want more SAT problems, then no, you don't. Should we try it again?
Ask us again.
No. You know my strategy. Oh, I should stop this. This is being recorded. Sorry.